Hey, doing? As Zach mentioned, my name is Corey Sullivan, ocean engineer. I've been working at Innovasea for 3 years now. Before that, I was working here as a research engineer. Really enjoy it based out of the Boston office and talk today about open ocean or offshore aquaculture. Rough outline, I'll give you an introduction on Innovasea, which is the company I work for. What is offshore aquaculture and why bother and why are we interested in it? Disciplines within aquaculture, I know there's a wide group here, so I'll do a little sidebar, say like other people that I work with. I'm an engineer, I'm usually there, but I work with a lot of different folks, so I'll talk about that a little bit. And then I'll go into sort of a broad brush vision of what's important to me and what design considerations I use in a net pen or a mooring design. And then I'll have a ton of answers and questions at the end. I have a lot of backup slides, so any really detailed questions, write them down and see if you can stop. So Innovasea, what are we trying to do? We are continuing to push to become the hatch to harvest solution provider for offshore aquaculture. I say offshore, we have a land-based division as well, but we have technology in hatchery, nursery. We have 2 divisions that cover a full grow-out of different fish species. The land-based unit based out of Baton Rouge and the open ocean aquaculture unit based out of here, Boston here. And we have harvest technologies for both of those. In recent years, what we've been trying to do is a big push towards precision aquaculture. A bit of a buzzword right now, but what it is trying to take information that you can get from sensors deployed in the field or from your field staff, interpret those inputs, make decisions, and act on them. For those who are familiar with farmers in general or aquaculture people in general, they got a really good gut feel. You know, if they think that something needs to happen, there's a good reason behind it. So what we're trying to do is bolster that with science-backed decision-making. We're not trying to supersede that. We're not trying to take anything away from you. But if you can act that much faster on something that you know you're going to have a gut feel on, that's what the push is in recent years. Little plug on just our experience. 8 offices, 25 plus years, over 700 installations. That covers all of our business units. So not just open aquaculture. We do not have 700 plus pens in the water. 25 plus countries and over 20 species that we are a part of. These are the 3 units that I work with most directly. Land-based aquaculture, they handle all of our nursery, hatchery, and recirculating aquaculture systems. Open ocean aquaculture, that's where I live. That's where I do all my work. And then aquaculture intelligence. Aquaculture intelligence is the unit that is so focused on building the sensors, acquiring the data, managing the data, and moving towards that decision-based operation that I talked about. Since I'm an open ocean aquaculture, I'm going to focus on that a little bit more. But again, any questions on anything else, I'll do my best to answer. So don't hold back on anything. Open ocean aquaculture, offshore aquaculture, depending on who you're talking to, it's referenced differently. But why farm there? First, a few definitions. I may get some eye rolls. There's a lot of ocean folks here, so give me a little bit of slack. This is within the aquaculture lens, how a lot of people treat this stuff. Offshore, anything a kilometer or greater. Open ocean, exposed to a wide fetch, so that's excluding anything in bays, fjords, anything that's protected or semi-protected. Then high energy, this is the one that I know a lot of you guys are going to scoff at. Anything above a significant wave height of 1 meter on average, or anything that has a consistent current observed of just over 20 centimeters per second. Seems like a really low threshold for a lot of people, but in the aquaculture space, that's when you start having to change how you're approaching your operations and your pen design as a whole. So that is when high energy is a very low bar to jump over. So why would we want to go to these high energy environments? Off the cuff, everyone just thinks of the negatives, which are shown here. It's inaccessible, there's a lot of destructive energy, and it's dangerous. People are going to have to be out there dealing with the conditions. Not a great example because I cropped it, but in the top right is a feeding operation in the middle of the ocean. There's no infrastructure around I think that's 7 miles offshore, and you're just arriving at a feed buoy to start your operation, compared to a semi-protected site in the bottom right where you're right behind the lee of the island. You can go get lunch over there, hang out, whatever you want to do. What is the drive to move to the offshore environments? There are numerous, but I'll hit a couple of them. So this is an example of the infrastructure required for like a RAS system. And again, not knocking my colleagues in the land-based system. There's a lot of benefits there too, but comparatively, I don't have to worry about filtration, gas management. I don't have to install all this infrastructure to get my exchanges to have a healthy grow out volume compared to a low energy site. Algae blooms are much lower in the open ocean when you're in a more exposed site due to that water exchange. relatively stable compared to, again, these lower energies, somewhat protected sites, which have big swings across a different season. Anyone who knows about the Great Bay here knows that it's a big variation from summer to winter. And then space for expansion. In a lot of places, when we're siting these open ocean farms, we're trying our hardest not to compete with other industries. So we're in a space that's relatively dead, and then there's room to expand within those spaces. So on the whole, there's a lot of pros. Maybe this list is a little bit colored because I'm biased. It's a very short cons list. But pros, there's a lot of, there's not as much energy input into managing your water and your managing your water delivery, feed delivery, things like that. Because you're in an open ocean environment and that flow through is constantly occurring, you can pack in fish a little bit tighter without sacrificing fish health. And that's a big thing as you start to scale. If you're not worried about, oh, this is a really tight packed pond because you have very limited water size, you can continue to grow. So your production at a large scale begins to look more and more appetizing, pun intended, for consumers. More consistent production. And then why Innovasea is here is appropriate tech can mitigate what a lot of people see as the biggest hurdle, which is hurricanes or other large weather events in the ocean. If you know what you're doing out there, and for us, the solution that is submersible tech, then you can avoid a lot of the pitfalls of being in the open ocean. Cons, there are a few here, but they're big ones. High startup costs. That remains to be one of the biggest barriers into open ocean stuff, is that the CapEx is big, and we know that, and we're working to try and bring that down. High expertise. So it's not just fish husbandry, harder to say than I thought, but also being able to operate offshore. So you're trying to merge someone who knows everything about fish and someone who maybe worked on an oil rig. There is a fine-tuning expertise there. As mentioned, we're working on technologies, and there's other groups. I don't want to just plug in Innovasea, even though it's on my shirt. They're all working to get better tech in the open ocean, but there's still very few, on the whole, large-scale open ocean farms that are successful to point to. So that's still developing and growing. And then costs are driven by feed. This is sort of across aquaculture as a whole for finfish aquaculture. And I should stop now. There's a lot of different aquaculture. I'm specifically focused on finfish. I should have said that at the beginning. Feed is one of your highest input costs, like across the board, no matter what. But when you're now having to load the feed onto vessels to get it offshore, and then you're delivering it to pens that are completely open, that becomes way more of like something that you're really focused on. So that's another point that people tend to look at as a negative on this. But on the whole, we're happy to be in the open ocean and continuing to look that way. Again, I mentioned it before, but submersible tech is the way that we're tackling this. So we put as much gear 10, 15 meters below the sea surface, anything that we can. We allow it to go up and down. Anything that's on the surface is robust and meant to be beat up. But that is how we're trying to tackle the entry into open ocean, and not just the submersible gear, but the ancillary systems. How do you connect your user, which primarily is going to be on the surface on a boat, to all your submerged infrastructure? So now I'll go into the little sidebar. I'll go into the engineering afterwards, but other technical disciplines that I work with, big list, electromechanical and software. There's a lot of guys that I work with that they're building these systems to help us monitor all our subsea infrastructure, whether it's building an array suite on the buoy systems, designing specific acoustic sensors, or down to the user display shown in the right here, where I can pull up an app on my phone and get all my sensor data back to us. And all that's really important, because if it's not easy to get the farmers who are going to be out in the middle of the ocean to check their stuff, they're just not going to use it. So this is extremely important for us to bridge that gap of introducing tech into what has predominantly been a manual field for many years. Machine learning, buzzword across, I think, every industry right now, but trying to get visual inputs and turn them into actionable outputs. The video here is a biomass estimator. So as fish go by the camera lens here, we have an algorithm that we are continuing to train, and it tells us how much biomass is estimated per fish. And on that, you can see how your cohort health is doing, whether your growth rates are low. You can look at your distribution, and in some cases, decide whether you can wait another week to harvest or not. And so all that is very important for the big operational costs it takes to to start a harvest or change your feeding operation, things like that. Biological sciences kind of goes without saying. We're in animal husbandry. There's innumerable. This is just a small snippet of what you could do from the biological sciences side. Production and hatchery managers, these are people making sure the fish are healthy, either from egg to grow up or in the nursery and hatchery, which is extremely important to make sure that by the time we get our fish from the hatchery to the ocean, that they're going to survive and grow in a robust manner. Fish health, biological sciences, and then we do some numerical modeling and actual testing as well. I make sure that in the center photo here, it's depositional modeling. I'm sure some people here are familiar with that, making sure that when we're introducing a new farm that we're not going to blow up the environment there. That's extremely important in the push to continue to make aquaculture as an industry much more sustainable. That's something we always target. And then what I do, which is mechanical and ocean engineering, structural design, stability analyses, dynamic analyses. We use Orcaflex up here in the top right, dynamic analysis software to get loads. So it's not just a static load that I'm interested in. I want to see what the waves and currents are going to do in the 50, 100, 200-year storm. And I also do a lot of mooring design personally. So I'm going to walk through a sort of a broad set of what I consider when I walk through a specific net pen or mooring design. I'm going to keep it relatively high level. There's a few things on the list that I'll go through. Looking at hydrostatics, will it float? Will it sink when I want it to? Strength, operational considerations, user feedback, and then design execution. And from a broad brush, and there's so many subheadings that I could put in here that it's just not worth it. But when I'm starting to either a new pen design or a new client who's interested in installing a fish farm, these are the things that I look at first. So quick information blurb on pen classification, fish pen classification. There's roughly four, I'm sure there's a lot of subsets now if you look around, but 4 types of fish pens that are in the ocean now. Gravity pens, which has a floating collar up top, and it is held open with a weight ring or other weight scenario down bottom to keep the net pen open. Anchor tension, which is a very fine-tuned anchor placement to keep any volume open. Semi-rigid, this is a sea station, one of our flagship pens. And that's sort of a combination. It's got a hard structure to it. It's not as flexible as a gravity pen, but it's not a fully rigid structure like the one at the right, which is an interesting example, but it's sort of based on like an oil rig design. There's a lot of massive, strong steel or other metal infrastructure, and that is how the pen survives versus utilizing different submerged techniques or other avenues. We have 3 of these classes. We have duck and cover style pens. So all of our pens are submersible with the exception of the Aquaspar. These are Seavolution pen, Sea Protean pen, 2 duck and cover style pens. That's traditional fish pen aquaculture that you would see like in Norway. Those big circular cages are very common when people think about aquaculture generally. We take that and make it such that if you're in an environment like Gulf of Mexico or Bay of La Paz, West Coast, where you might see hurricanes or other large storms, when something's coming, you sink it down below the sea level. Aquaspar, center one here, it's a tension leg. That is used primarily in protected waters or riverways at a spot that we can get really fine-tuned anchor deployments without worry about the installation cost because of how complex it is to get those anchors to just the right place. And then semi-rigid sea station. I just like that shot. I think it's really cool. Divers swimming away from the pen. And that has one of the best track records of offshore fish pens in the world and continues to be one of the pens that we look to in a very extreme environment. So from a design input standpoint, someone comes to me and says they want a new fish farm, new fish pen. There's a lot of considerations that I need to bring into the fold. First thing is size. How big are the pens? How many pens do you want? And overall, like what's your area looking like? Location, that includes water depth, and then the environmental inputs, currents and waves. Those inputs will allow me to choose from our suite of pens what type is going to be needed at that site. If it's a really high wave environment site that you really want to be operating at the surface, push it towards sea station. If it's something a little calmer, if you can get to a duck and cover style pen, that's what we like to target because it is just so much easier on that operational side. You can get people on the deck doing operations and not have to worry about as much infrastructure needed to get down to the subsurface. Fish species, and there's a slew of reasons we need this. One of the most important that I think about is netting parameters. Every different species has a different net style that they need. Some fish will bite through a certain type of net. They rub up against it, they damage it. They need small mesh, big mesh, all different options for that. Drives sort of which pen we can put a certain type of netting on, or how we work that into existing designs. I'm not clicking my clicker in time. And then accessory components. This is something that I've found that a lot of people tend to kind of look over. You have your pen design, you manage it by yourself, you're doing the analysis, hydrostatics look good, everyone's happy. You start adding all these components without really thinking about how it affects the overall design. So understanding from the beginning what things are needed on the pen drive either the size of the pen, different operational considerations. Do I need a new pen design? I don't often get the leeway to say, hey, let's go build a new pen. But when I do, it's really cool. I need this list to say why none of these work for a pen that we have, or if it's just a good avenue for us to explore the next generation. So taking these set of inputs from the client, from the user, from the inquiry is how I move to the next step of design. Looking at a C station for an example, I'll talk about the hydrostatics. And so C station is an interesting pen. It's composed of two big parts. It has a spar in the middle, and then around that spar is a rim. It's sort of like a bicycle wheel, and then there's tension members between it. So bicycle with spokes, that's generally the idea of a C station and how the theory works. I'm looking at Zach because he was part of the early designs of C station. Is that a yes or no? And a C station, this pen lives on or near the bottom a lot of the time. So, but we need it to work at the surface just as well for other operations. So in a C station, we have two types of buoyancy on it. We have a static buoyancy, which is something that never changes. In this case, in the top of the spar, it's just a closed chamber. Nothing goes in or out, it's closed air volume that keeps it stable and gives us enough buoyancy when it's submerged that it's not going to bounce off the bottom. When we want it to go to the bottom, we flood the bottom chamber in my crude cartoon on the right there. And the whole system drops to the bottom until that block, which is a pendant weight, hits the bottom. And then on the whole, the pen itself above the pendant weight is positively buoyant. And I want it to stay in that spot at any given time. And so when I'm doing pen design in submersible pen aquaculture, it's not just load it up with buoyancy and you're happy because it's going to stay on the surface. It's a fine-tuning balance of how do I want it to behave on the surface, and then at the bottom, in particular, like I said, we don't want it bouncing off the bottom under high currents, big waves, anything like that. So that's always something that I continue to come back to. Almost every design iteration that I go through, any addition, any update, we got to go all the way back to hydrostatics every single time to make sure that we're in that working regime. Oceanographic conditions assessment again. So the ocean is not static. You're all fine and good that it's going to float when it's flat, but you want to make sure that it's going to work out in real conditions as well. In order of my personal weighting of environmental conditions, I look at currents, waves, and winds. The reason that I put currents higher is that typically they're on longer time scales and they're more consistent than a periodic wave loading. So that tends to raise my peak tensions more than just a wave loading on its own. So I put that up top, waves. So we're in submersible tech for a reason. The diagram in the bottom right shows you the decrease in particle velocity and wave energy as you increase with depth. So that's why we're at the bottom anyways. As a submersible pen designer, I'm a little bit of a happier camper than if I'm trying to put something up at the water line where it's going to get absolutely demolished by waves as they come through. Winds, I don't look at as much, but for all of the appurtenant structures, all the add-on structures, where there's feed barges, buoys, things like that, that's where the wind loading becomes a much bigger effect, because in that case, there's only this much, maybe 6-8 feet for some feed vessels that is below the water level, but you have such a large windage in those cases that you want to make sure that that is taken into consideration depending on what you're looking at. I look at these in 3 load cases when I do a design operational load case, which is, in my case, the absolute peak that anybody wants to be doing regular operations on a farm. You talk to any aquaculture farmer, there's going to be a size wave or a current or a wind that they're going to say, we're not even going to bother going out. but I need my pens to operate at their maximum efficiency up to that point without detriment to their operations. So that is the target that I'm. Extreme or design storm. This is my 25-year, my 50-year, my 100-year return storm that, if one of these occurs, I need everything on the farm to maintain its structural integrity without change to it once that storm passes. And then the next step is that survival storm. We get the biggest hurricane ever recorded. I need to understand how stuff's going to break, how it might fail, whether that's absolutely catastrophic, and how do I mitigate that on a broad scale. So I mentioned waves that, the reason that we're in submersible tech a lot of the times is to get away from that surface energy. As an example of this, this is a partner farm of ours in Miramar, Panama. It's on the Gulf, on the Caribbean seaside. And this is 3 years data, was 2014 to 2017. And the average significant wave height across this period is 1.5 meters. Doesn't seem like much, but when you look at the actual red line, pretty frequently we're up above that 3 meter significant wave height line over this 3-year span. And if you look at the blue line, which is the maximum wave height recorded during those times, we're up above 5 meters. I don't want to say regularly because it's a long time scale, but a good amount of time. So this is something that we're always considering too. It was second on my list, but it's still of utmost importance of what I'm looking at when designing fish pens. This is an example of a buoy at about 12 meters below the sea surface in a 1 meter sea, which most of us would be, relatively minor. And then you see the divers there just getting absolutely snapped around. And this isn't at the surface. This is, you should be out of a good chunk of the energy there, but as you can see, they're having a blast, but this is their job. So, but it's that consideration that we always are continuing to look at as well. So if I take an example pen, duck and cover style pen at the surface, we have a float collar up top, a sinker tube, and some pen and weights down below. My next step after assessing those environmental conditions is looking at a quasi-static load analysis. And I'll look at that from a global scale on the pen and then pick out individual components that I'm concerned about for that pen. And then this will go through like absolute Rev 1, whiteboard sketch, down to Rev 2 or 3 based on those quasi-static inputs. But that's just step 1 of my structural strength analysis. Next step is sort of the meat for me, is the dynamic analyses. We work in a program called Orcaflex, came out of oil and gas, really good at ropes, pipes, and representations of those, and good at running waves, currents, winds at those scenarios and providing reasonable outputs to us. So I'll take that pen model, say we build a CAD program, I have to translate that into a representative model. I can't just put it right in eye for eye. That model will take decades to run on the computing power that we have. So we make a representative model, build it out, and then I'll run those series of operational, extreme, and survival load cases on this. And this is where the final output from this is an executable design. It's however many times I do this, changing how thick my pad eye is, how much buoyancy I need. Maybe my pen's starting to bounce off the bottom in the submerged case. After this is kind of where we're ready to. We could produce this pen if we wanted to, but that is. We don't do that. And the reason is that there's 2 really big pieces of pen design, and for those engineers out there, just general design, that if you don't talk to who's going to make it or who's going to use it, they're going to be bummed at you. So you can't just blast your way through a really innovative idea, especially when you're working in the open ocean with people who are saltiest you ever met, and say, yep, we're going to do this. I made this on my computer. It's all fine. You have to work with those folks on how things are getting made, making sure that it's easy, cost-effective, repeatable, and that's a big one. If I go to Zach one day and he's like, oh yeah, I can make that, no problem. I go to Rob the next month and he's like, oh no, I can't do it that way. Zach had some special tool. You're always trying to improve that design for manufacturing, and that's something that I think more of a broad engineering point there, but very important. And then our biggest allies in this are our guys in the field. We're lucky that we actually have research dive teams and development teams at 2 of our partner farms. This is Gorka and Juan Carlos on the left, and they are the men. They are awesome. They're looking happy here, but In the meeting before that, they were saying this. They were like, you have no idea what you're talking about. You're not listening to us. And that's why it's so important that if you want engagement, particularly with where we're at now, trying to push into precision aquaculture. So we are, in a lot of ways, changing how they've done things, where they see with their eyes, they feel when they're in the water, and they're making decisions that way. If you don't have buy-in on the front end, they just won't use stuff. They will let that buoy in the background sit and rust on the side of their boat while they jump in the water and do it. So it's not just getting their feedback on certain things, because they've both been in aquaculture for decades now, and they have a certain way of doing it. If you don't push on them a little bit, they'll never get out of that and try something new. But if you don't get their buy-in on the front end, then they really will just let things sit and rust in the yard. They'll take it off the boat. They won't tell you. They'll hide it. That is, for me recently in particular, has been the most important aspect of design, is getting that buy-in from front to end, and making sure they're involved along the way. So you're not making from going down the path 5 miles the wrong way. I want them to tell me ahead of time. So from the design cycle, from a fish pen perspective, what I'm looking for is hydrostatic stability, dynamic stability, structural integrity. I don't want things to break, lifetime and serviceability, and component interfacing fittings. And so these are 3 of the fish pen that we develop. Top left is the Evolution pen, which is primarily done in La Paz, Mexico, snapper and Tatuaba. And they love these pens. They're on the surface 80% of the time, but when it comes into hurricane season, they just sink them and don't worry about them. Sea Station in the bottom left, and then our newest pen, the Sea Protean, on the right there, which is still in development. Just a snapshot of those. And then from a mooring design consideration, I didn't talk much about that. Fish pen design is a little bit more interesting from a broad perspective, but I go through the same set of steps when I'm doing a mooring design. And the outputs are a large grid system maintaining sometimes up to 20 fish pens at a time. I'm looking at rope strength, the steel component strength, anchor pullout. And for a mooring system, it's not about if it fails, it's about when and how it fails for a lot of people. And it's, can you design a specific fuse? Do you want a fuse? Where is that fuse? And how easy is it to fix that fuse? And so that's something that I'm always standing up on a pedestal yelling, tell me about things so I can do the mooring. But everyone, it's sort of that last piece design, but it is also very important to make sure that our pens aren't going anywhere and our stock is safe. These are just some of the components, and just sort of a snapshot of what I'm looking at. There's probably 8 individual full assemblies, line assemblies that go into any of the grid mooring systems, just making sure that they're all optimized and designed to survive exposure. This is a fly-through of an example of one of our fish pen designs. Just a Sea Station grid. Just a cool fly through generally. And this is my last official slide. I realized partway through that I've been absolutely cruising. So apologies if I was motoring through stuff, but we have a lot of time for questions if anybody has something.
For that example that you showed, how long would that take to deploy and set up the mooring and develop config?
So if I'm doing a grid mooring system, like a 2x5, like this, we can deploy this. If we have a dedicated team over the course of like 2 weeks, maybe, but realistically to final tensioning, it's about a month. And a lot of it is, they got to load up maybe 2 anchors at a time, depending on how big your vessel is. Going out to the site, dropping it, setting preliminary sites, and then they're back. So on a good day, they can maybe get 4 anchors installed and properly set in location.
Is there an onboard power supply? How do you do the buoyancy? compensation?
So all of our pens are just air driven. So air compressors on a vessel, it can be a little, little dinghy or up to the large feed vessel. And a lot of that is just pulling up and turning on a valve, hooking up to the compressor.
So no onboard power at all.
And our fish pens, nope, we're trying to keep them, I'm going to say dumb, but we try to keep them as dumb as possible so that in an event of some sort of emergency, that it's, it's not a failure of an electronic system that makes the pen fail.
That's not even lights when you have to be on the surface.
In our case, I think we're below the thresholds of the need. We actually have a site in Hawaii that's relatively close to Tacoma Airport, and the FAA didn't say we had to put anything on it. So it's for now, we don't have anything on there, but on a grid system, so at the corners of this, we would have a lighted, a set of lighted buoys in that case.
I was just wondering that, given the motion, you may have a nice wave-induced power source there that could.
Yeah, and that's something that we are not developing it ourselves. We are keeping an eye on a lot of the research that's going on to have some small discretized, whether it's wave buoys, we use a lot of solar, but something else to provide whether power to our sensors, our subsea sensors. That's a big thing that we're keeping an eye on.
I know this isn't your area, but you've been doing this, you and your company, you've been doing this long enough in enough places that I'm curious. Have you sensed a change in the acceptability of ocean farming over time? And also in different countries, is there more or less acceptability of it? I live on the coast of Maine,
Yeah.
and it's always, you can't encroach on the lobstermen and all that sort of thing. So there's always that kind of resistance. Could you just comment on changes that you've seen?
Yeah, definitely.
In time and geography?
Yeah, I think generally it feels a little bit cyclical, but I think on the whole, we're starting to see improvements across the board. And it's a lot of just, I don't want to say just marketing, but like us pushing, like there is a sustainable aquaculture. Aquaculture, a lot of people default to tiny ponds and fish that can't move and things like that. And it's informed, real responses to that. We can have fish that are growing in a great space and that kind of thing. In different countries, I would say they're more open to it compared to the United States. And that is definitely regional. There's a big push in different spots, but a lot of our partner farms, we have 2 partner farms, one in Mexico, one in Panama, and then we have the partner farm in Hawaii. And it's much easier for them to expand and for other people to get into the industry nearby us in the different countries. And hopefully, though, we're working towards getting some more acceptance of finfish. And I will say that broadly, finfish is probably of all of the aquaculture that you can attack, finfish is the one that has the biggest target on its back.
So I think it was on your very first slide in the kind of image that was the overview of everything. There was, I think, an ROV or an UV in there.
Yes.
What kind of underwater robotics do you have in the works besides the machine learning for biomass?
So for us right now, a lot of it is inspection style. So in the United States in particular, and a lot of more developed countries, diver time is super expensive. So that's a lot of what we're using it now for, is true, just sort of traditional ROV inspection style. We are working on net cleaning ROVs or AUVs. The Sea Station in particular is posing a challenge for us, especially because it's not a traditional vertical net wall, but that's something we're continuing to work on. And it's not our expertise, so we're partnering with those who live in that space and then just providing our input to them.
I know this isn't technically what you focused on in the presentation, but I was just curious, what does like the permitting look like for something like this? Like, are you deploying in international water? I don't understand anything about this.
In a word, nightmarish. No, it's a long process. In all of our sites right now that we work on, they are all within the country, EEZ. We are not outside of that in international waters, something like that. In Hawaii, that farm is in state waters versus federal waters. So it really depends on sort of who's more apt to to help you work through the permitting pathway as opposed to through up roadblocks. Yeah, so it's a long process, but you really have to have your ducks in a row. You gotta, a lot of times I'm doing a full mooring design before I know everything and having to explain why this is the right way to go about it, and explaining the gear. And then there's so many iterations of reviews and defenses, and there's public forums like this as well. And it's definitely a lattice of work, and it's similar everywhere, but in the United States in particular right now, the pathway isn't super clear, so you're sort of snaking your way around.
Gotcha, thank you.
What's the failure rate on those structures? Like, how often do they actually break apart or fail in other means?
For ours, we're looking at low. Sea Station in particular we have some of our longest deployed pens just past 10 years. And that is our target design life for our structures in a lot of places. And so then it's a reinspection that comes out of the water and a re-review, and it's either a certification or a retirement. And so that is where we're at. With some of the pens that we've been developing, there's componentry failure, but in terms of a full pen, we've never had a full pen failure in our commercial farms.
Are there like diver imposed limitations on where you're able to install these? And I guess, do you think in the future ROVs might expand or allow you to deploy in areas that maybe diver limitations wouldn't let you?
Yeah, definitely. So there's a couple limitations. There is just a general cost depth limitation. So that kind of puts us in a certain area that we wouldn't go beyond just because the cost of the mooring lines. But in general, we are trying to move away from diverless anything. So yeah, ROV, stuff that's connected to the surface, AUV, all of it is definitely on the table right now. The CapEx cost to get into that space in a lot of locations doesn't outweigh just having a big dive staff to be able to handle that. So it is definitely where the industry is going, especially for places, again, like Norway has a really robust aquaculture industry, and they don't put divers in the water because a Norwegian diver is very expensive. So it's bringing that to everywhere is definitely the next step. In terms of a limitation, some localities have them. We have farm limitations, and then we have our research limitations, but some of those are more self-imposed as opposed to true limitations.
What's your typical consumer who's buying this?
Honestly, it's a great question. It's people who are interested in aquaculture. Either they are adjacent, they work in the ocean and they're familiar with aquaculture, they're interested in it. You get a lot of people that do move it in through different ocean industries. We have a lot of ex-fishermen that come to this stuff, but for a big capital expenditure like this, it's a lot of times it's a consortium. It's groups of, I got my fish guy, I got my offshore guy, and then the bank account behind it, or some combination of those. It's not typically a single entity.
How do you get the fish out?
I get the fish out. So in this one, I'm gonna see if I have a backup slide. This might be the first one I have a backup slide for. I was not. I was so ready for a backup slide here. So let's go to the closest one. So in Sea Station in particular is the most interesting one. We'll put in a secondary net. In this case, it's sort of an inverse of the cone, just a smaller version, and we use the submersibility of the pens to crowd the fish into a location. So Sea Station will sink it, drop a little bit of feed, crowd the fish into the location, get it up, and then we use a pumping system to get them onto the vessel through a dewatering table and then into exacting tanks, which then are transported to shore. In other places, it's all sort of a version of crowding in some way. You have sweep seine nets where you kind of like fold it around and crowd fish into the location. You have true purse seine nets that some people use. It definitely varies on the type, the depth, and how much fish you're trying to get out of it at a time.
I'm sure this is not on your side of thing, but you might know.
Ask them all. Let's see if I can try and stump me.
I'm curious about the ecological side effects. Like, are they choosing the fish based on the location? So not to have massive issues.
Yes,
It could be
definitely.
natural, ecological disaster because the fish are going to be reproducing to some extent, I assume.
So most of them are not. They're sterile in some cases. This is where I'm not going to say some of the buzzwords that are in my head because I know I'm probably going to misspeak, but they are in most cases sterile and they cannot reproduce. And how they achieve that, I will defer on that. But in terms of what type of fish, yes, that does matter. So you can, like, if a fish is not nearly native to a space, it's extremely difficult to try and go through that permitting pathway, and that in and of itself is enough to direct you to a more hospitable species to that location.
Is it profitable?
Profitable. It can be. Again, there are farms that are profitable out there. It's definitely an economy of scale thing. Hawaii farm I know is profitable for us. The Mexico farm is up there as well. And a lot of it is we're marching towards that as an industry. You get a lot of people who are in the growth period right now too. So they've gotten 2 to 3 pens. They have their operations nailed, and they're coming back and ready to purchase additional pens to grow into that large commercial scale that can continue to feed back into it. All the way back.
I was just wondering, you said the lifetime of the pens is about 10 years. Are you intending to keep them 10 years in the same spot, or do they move also to minimize environmental impact?
So in these cases, when we do a site assessment, we do the depositional modeling of a site to ensure that the farm as it exists there, sorry, I was looking for the snippet, but it's here. When you do this depositional modeling, we're doing that to get the best site to have the least amount of impact on a site. So we're not typically moving pens. That has been brought up as an option for some places. When you trying to get to commercial scale, it's just not tenable to try and have something that's constantly moving. But in some cases, like in the Chilean market, for example, they will, because they're in very tight fjords or in very small, narrow byways, they will move those around. And that's a function of not as much water exchange compared to an open ocean site, which disperses much more readily.
How do you usually pick sites? There's like a consortium and someone who's interested in operating one kind of suggest a site, or do you guys kind of suggest a site and look for a consortium who's interested?
We have both. We have some people who say, we have no idea, but we have this region that we're sort of interested in, and we'll do a very detailed site selection. There's a group with NOAA that does that specializes that in the United States that helps filter out high use areas, fishing, recreation, things like that. And then for those guys that don't have that readily available, sometimes they do come with a permitted site. There's a couple places we're talking to in Europe, I'll just say Europe, that have sites ready, and then we're building to fit those sites. And then on the flip side, they say, we have no idea, we've gotten general approval, can you help us pick a site? So, and that's where we'll look at, from my standpoint, waves, currents, drag, make sure there's enough depth, depositional modeling to make sure that we're not, again, doing anything detrimental to that location, that kind of thing.
Can I ask a second question?
Yeah.
Do you get a lot of interest from like companies and institutions that produce a lot of fish already, or does it tend to be people who, in organizations that don't produce a lot of fish in like a more traditional Delta setting?
And Innovasea in particular recently has been getting a lot of interest from people who have established farms, and for reasons of either their pens aren't lasting the amount of time that they're expected, or in general, there is a big push across industry to move to a submersible aquaculture. Whether that's for increased lifetime, or in a lot of cases, it's for visual aspect, being able to submerge your pen. You get a lot of the not in my backyard NIMBY folks that they don't want to see fish pens, and however small they are going to be on the horizon, but being able to say, nope, they're gone. Most of the time they're down is becoming very attractive to a lot of locales.
Gotcha. Is that relationship between like companies that already have produced some amount of fish and maybe are a little bit more cost a little bit more concerned about like managing a budget. Is that a hard relationship to manage, or is it just the same as anything else from a cost perspective?
A little bit. It's always a working relationship. You come in, you get your first quote, and then it's like, okay, like let's talk about it. It's, and we, that's what we try to do is work with folks. We know that it's a big swing in a lot of cases. So it's not, here's a quote, yes or no, we'll see you later. It's oftentimes it's a working relationship on how we can find it.
Gotcha.
How much do the drag forces on a fish pen change over the life of the pen with biofouling?
So biofouling is the bane of my existence. It can go, when we look at net drag, the occlusion of the net is so critical to how much drag that is. So I couldn't put a number on it, but it's hugely important. And we use a type of net mesh that is generally resistant to fouling in a lot of locations. It is more expensive, but in terms of the savings you can get on not having to send divers down and do that, it's a big change. We have some pens that are older, or maybe they've not been populated for a while, and getting those done, those things see some serious forces on that. So you're going from something porous to almost a flat sheet in some cases.
I think more of a biological sense. You said during something like hurricane events, you sink them.
Yep.
Have you experienced any loss in like fish stock of the
No, so sorry, any loss of
in the species?
No, so we make sure that most species are readily available to accept a change in depth. However, there are some species that do have sensitive air bladders, and in that case, it's all about managing the speed of the ascent. So we rarely see an actual mortality event due to just raising or lowering. It's if something were to happen or improperly managed, that it rockets to the surface or something like that. Even with salmonids that a lot of times will need to gulp air, there's been studies that have done that they can stay down for 2 weeks at a time in some cases and not detrimentally affect the actual growth of that fish. So something we are definitely cognizant of, and there are certain species that are very critical at how fast you move it up and down, but on the whole, not that.
So regarding raising and lowering them, I'm assuming since there's not power on board, you don't have like a local accelerometer or wave sensor to alert you to raise or lower it. So are you relying on local forecasting offices, or do you have like within the consortium, somebody has wave buoy nearby?
Yeah, so we personally, we just deployed a new full suite sensor buoy in Hawaii, and our AQI office, the Aquaculture Intelligence Office, they manage a lot of that data. So we are live streaming to our cloud servers, and then it's literally an app that can tell you. Right now, we are still working on the real triggers, but what we have now is that with typically standard forecasting, but also with the live data streams that our farm managers, the feed managers, everyone can pull it up on their phone simultaneously and make those calls. So right now, we are still relying a lot on the expertise. They can just get that information faster.
Question, is that wave data free to the public, or is it just within the people that are collecting it?
Right now, we are in the development stage of a certain sensor, so it is not being published here.
Good question.
How do you link the structural analysis to the dynamic analysis? Where's that process?
Oh yeah, so when I do a dynamic analysis, again, we have that representative model. The output from that are the tensions or the loads on particular pieces of the pen, and then I'll bring those into a more detailed, localized analysis. On that slide, there was, maybe not. I do a finite element analysis or even set of hand calculations with those new inputs. So it's not one-to-one, but it's bringing those outputs and applying them to a more detailed analysis of the components to make sure that they can withstand the loads from that new dynamic analysis.
Any last questions?
So you have the deposition modeling there,
Yes.
right? So there's another waste product that comes out, especially when you have a 2x5 net pen with, I don't know how much biomass you have in there, but what about the nitrogen wastes? Are there any issues with getting your permits at some of these sites with respect to nitrogen?
Yeah. So as part of any permitting application or our site selection, we do, and I don't do it personally, so it'll be a little bit broad brush, but we do have to express that balance in what it is and ensure with the environmental conditions at that site that the dispersion is appropriate, that it's not localized and resulting in like a eutrophication event or something like that.
Has there been any discussions about in the permitting process with respect to how a wastewater treatment plant is permitted with flows and initial zone of dilutions and far field characteristics with respect to almost a point source?
That's a great question, and if it's not, then it's something that we should definitely look into.
Just curious, what have you observed?
Myself personally, I've not seen any direct correlations to that. I know that we do get a lot of wastewater folks that come into this to help us do our calculations, but I haven't seen a direct reference to any of those when in the permit.
Are all these farms in mostly blue water?
Most of them are. This example, I don't actually know what this is not, but a lot of them are, yeah. A lot of what we're permitting with the submersible pen, we need the depth.
So what do fish normally do in a wave event or a hurricane? Do they evacuate or do they stay and just deal with the conditions? Because in an aquaculture farm, they have to deal with the conditions.
That's a good question. I think a lot of it at the depths that we typically have pens, they're low enough that it's not appreciable, but I cannot say.
Deep you said?
So the grid plane in this perspective is about 15 meters below the seawater. And then the base of the pen in the submerged state is typically somewhere below that. Depends on what the water level is, but.
So the high frequency stuff is mostly above them, but there might be some swell motion.
Yeah, some small stuff, which is much more readily taken on by the.
Dealt with, yeah. Okay.